Hello, everybody, and welcome to Physical Chemistry. So today we're going to be diving a little bit more into the nuances of quantum mechanical operators by talking about one very important feature of a quantum mechanical operator. And that's that every single one of them is something called a Hermitian operator. So this is kind of an advanced mathematical terminology. But one of the good ways to try and describe a Hermitian operator is to a certain extent saying that we can be a little bit lax about order of operations. So, order of operations are incredibly important in operator mechanics. But one of the things that should hold when dealing with quantum mechanical operators is that if I apply my operator to a wave function and then apply its complex conjugate, this will actually be the same thing as applying as applying my operator to what was originally my complex conjugate, and then applying the complex conjugate of my reverse operator, and then taking the whole thing to a complex conjugate. And this can be a little bit odd, but a simpler way of looking at it is that I can go ahead and switch my first and second wave function. And doing so will only change the overall result by a complex conjugate. So again, this will only have a real impact if we end up with an imaginary result, which hopefully should be very rarely the case when trying to apply a set of operators. So the complex conjugate carried along here at the end is often a little bit unnecessary, but it does play its role occasionally, so it's important to include it. Now, one of the important things is let's go ahead and take a look at what this kind of should really look like if I'm dealing with an eigenvalue system. So, not just an overall operator, but an operator that generates an eigenvalue. Well, if I go ahead and apply my omega operator, I should go ahead and get the omega value for the eigenvalue of system I. Because I apply my operator to I get the eigenvalue of I. Now, since an eigenvalue is a value and has no x variables present in it, that means I can bring it outside of the integral. And since I can bring it outside of the integral, well, what this ends up meaning is that I can go ahead and raise everything inside to the complex conjugate. And since these are two functions, they should essentially be commutable. So I can go ahead and switch the order of the functions and then apply complex conjugate to everybody. So essentially just flip the signs of uh, any imaginary numbers. And each one of these steps should be fairly robust. So again, if I have a system that generates a real eigenvalue, it should be hypothetically Hermitian. Now, one of the easier ways to try and illustrate this is what it looks like in Dirac notation. So in Dirac notation, one way we can go ahead and explain this is again, all I'm doing is simply switching my two wave functions, and doing so results in the introduction of a complex conjugate. And again, that would be this first step. And we can also represent the second step also in Dirac notation. If I apply my wave function, this generates uh, a real eigenvalue of the system on the left. And as long as these two values are, and then by definition, I should be able to switch the order of these two wave functions as long as I flip the complex conjugate. Now, one of the very interesting factors is that if I was going to apply this operator here on the right, well, this would be the same thing as generating the eigenfunction of the eigenvalue of my wave function f to the complex conjugate. So what this ends up showing me is a side benefit if I have a Hermitian operator, which all quantum mechanical operators are, that these two equations should be equivalent. So that the eigenvalue for I times this cross product should be the same thing as the complex conjugate of the eigenvalue for f times times this cross product. Now, this is going to have some interesting implications that we're going to go ahead and try and dive into a little bit here. So let's go ahead and kind of, first of all, illustrate that all of our quantum mechanical operators are Hermitian. Now, I can do this by proving that both the position operator and the momentum operator are Hermitian. If both of these individual operators are Hermitian, then anything composed of these operators should be Hermitian. So in other words, if I can prove that both of these individual operators are Hermitian, it proves that all quantum mechanical operators will be Hermitian. So let's go ahead and do this with X. This isn't actually too bad. So again, in Dirac notation, wave function of F applied to the position operator times the wave function of I. Again, this will all be within an integral. Now, because X should be commutable with any other mathematical function, I can go ahead and pull X out front. And then this allows me to rearrange my two wave functions. So rearrange the two wave functions. That should be fine. Then I can go ahead and raise the whole thing to a complex conjugate. So this means I'm just going to flip the sign on any imaginary numbers. So I do that on X. X remains unchanged. Do that to I, becomes a complex conjugate. Do that to F. Remove the complex conjugate because I just added another negative. Now, because X is still commutable, I can bring it back down here to the middle. And then this helps show that the position operator should be Hermitian, as if I flip the two wave functions, all this does is introduce a complex conjugate. So this is actually fairly cool and fairly useful. That's half of the problem solved. However, proving that it's the case for momentum is a little bit trickier, and we're gonna have to use integration by parts. I know, that great boogeyman of calculus. So first of all, let's go ahead and set up our equation. So we are going to start by applying our momentum operator to our wave function I, and then applying our second wave function as a complex conjugate. So we're going to start by inserting our Hermitian operator. Well, h bar I can go ahead and come out front because it's a constant. And then what this leaves me with is a derivative. Now, this gets a little bit annoying because, well, trying to do an integral of a derivative gets a little bit messy when you're trying to do it in general. So what we can then do is try and solve the system, again, by parts. Whereas if I go ahead and first do the first part, then it's going to be ddx dx, which essentially is just going to give me a 1 value. And then all I'm left with is the integral of my two wave functions times my constant. And again, we can go ahead and turn this into a discrete value. Then what I'm left with is essentially the flipped version of this derivative. So again, this kind of gets me most of the way that I'm after, because you'll notice that we did successfully switch the order of my two wave functions. The wave function f is now being acted on, and we're then applying our wave function I. Now, this only leaves me with this little crucial mess of I need to figure out what this guy is. So here you're going to have to take it on parts, or take it on faith, that this first set of integrals is going to be equal to 0 if I and j are different. So if these two functions are identical, well, then hopefully my function is normalized, and this would be 1, because I'm integrating over all space. Unfortunately, it turns out, via a trick I will show you later, that if these two functions are different, then this will actually go to 0. So if I have two different wave functions, then this one will go to 0. And then this leaves me with a little bit more of a simpler system where I'm now applying. I can now bring my negative h bar I inside my wave function. And then we're going to essentially have to, then what we'll find is that this is going to be the same thing as, you'll notice that this function is now the same thing as the negative of the momentum operator. But since it has an imaginary number, the negative of the momentum operator is also known as the complex conjugate of the momentum operator, which means that if I then apply the complex conjugate to this whole function, well, then I'm going to turn this first function into a complex conjugate, and I'm going to remove the complex conjugate on my momentum operator and on my wave function f. And when I do this, what I have now generated is the complex conjugate of my original wave function, where I've now just flipped f for I, so switched it around. So this is actually, again, the very definition of a Hermitian operator. So this is actually a fairly useful feature of wave functions because, again, it lets me, gives me a little bit more flexibility in the order of which I apply my operators. However, we're going to have, and we're going to make use of this as we go on throughout the course. However, we did make one major assumption here, and that's the fact that if I have the integral of my two wave functions, if they're non-identical, then they go to 0. Now, this is also known as a system being orthogonal. So a set of wave functions is said to be orthogonal if this is the case. So then what we are left with is proving that any set of eigenfunctions of her Hermitian operator are orthogonal. So if I have any eigenfunctions, if I have any set of wave functions that are the eigenfunction of any Hermitian operator, that will by definition prove that they're orthogonal. So this means that all I need to make sure is that I'm dealing with a eigenfunction, that my wave function is an eigenfunction of the position operator, the momentum operator, or the energy operator. If it's an eigenfunction of any of those operators, it means it's by definition orthogonal. And we're going to be making use of the orthogonality definition quite frequently throughout this course, as it quickly is going to become one of our big underpinnings of a lot of our equations. It's one of the more useful relationships in quantum mechanics. So in order to prove that a system is going to be orthogonal, well, let's go ahead and bust out our general set of wave functions. So I can go ahead and start with the assumption that two wave functions are going to be Hermitian. So it doesn't matter what what the operator is, as long as they're eigenfunctions and it's a Hermitian operator. Position, momentum, energy doesn't matter. So I can start with my definition of a system being Hermitian, and then I can go ahead and use the definition that both of these are eigenvalues. So if I apply my omega operator to my wave function, I'll end up generating an eigenvalue over here. So an eigenvalue of I, and then an eigenvalue of f. Then what I'm going to want to do is, since this is an eigenvalue, I'll bring it outside of the integral, and I'll do the same thing over here with the eigenvalue of f. However, make note that if I'm bringing it outside of the integral, I also need to apply my complex conjugate. So now what we're left with is that, this complex conjugate of the eigenvalue of f times, let's be honest, this little bit messy system. However, we've already shown that the complex conjugate of this integral will be the same thing as just flipping the order of operations. So now we're left with the wave function, complex conjugate of the wave function of f times the wave function of I. Now you'll notice that this means that we have two shared wave functions over here, and the only difference is going to be our eigenvalues. So what we can then do is take this whole expression on the right, move it over to combine with the expression on the left. And since they share a set of wave functions, I can collapse that down to a single expression. However, since the eigenvalues differ, what I'm left with is the difference in between my eigenvalue of I and the complex conjugate of the eigenvalue of f. Now, this seems a little bit much, but what this really helps show is that if I'm dealing with the eigenfunction of a Hermitian operator, one of two things must be true. Either these two eigenvalues have to be identical, because if these two are identical, then it goes to 0, and then this whole left-hand side goes to 0. However, if I'm dealing with a system where these are different eigenvalues, well, then congratulations. This integral has to go to 0. And this is really what we're showing with orthogonality, is that this equation, or this integral, should go to 0 as long as I doesn't equal to f. And so this leaves us with a wonderful set, a wonderful general expression. Any member of an eigenfunction set. So as long as I've got any set of eigenfunctions of a common operator, they will all be orthogonal. So let's go ahead and go back to, say, our, if I have a particle in between 0 and L. We showed that two possible solutions are sine pi x over L and sine 2 pi x over L. So since both of these are going to be an eigenfunction of the Hamiltonian, this means that these two will be orthogonal. Let's go ahead and illustrate this in kind of a more concrete example. So we're going to go ahead and start with our Dirac notation. So applying the sine 2 pi x to the sine pi x. Since there's no imaginary numbers, we don't have to deal with the complex conjugates. It's fairly nice and simple. So what we illustrate here is that if I integrate the system from 0 to L, which again is where these wave functions exist, then this should be equal to 0. Now let's go ahead and do this by a little bit of proof. So there is indeed a pre-solved integral that you can find in your integral tables for this general expression. And unfortunately, it is a little bit messy. So we can go ahead and simplify this general relationship, where again, you'll notice that mostly what we're doing is it's the difference in between subtracting the inner part of the two signs, again, normalized, versus adding the inner part of the two signs. So when we do this, what we end up with is sine pi x over L over 2 pi L from 0 to L. And then the same thing with 3 pi x. Again, minus and plus, so pi and 3 pi. Now, when we go ahead and do this, we now need to solve from 0 to L. So for the L case, x over L, this will just be 1. So sine of 1, or sine of pi, is 0. Then we have x goes to 0, sine of 0 is 0. How about sine of 3 pi? Well, that's also 0, and sine of 0 is 0. So each one of these terms will end up going to 0. And you can actually prove that this will happen with any integer value of pi, because what you'll be left with is an integer value of pi going from 0 to L, which means that each one of these signs will eventually go to 0, proving that the whole set of eigenfunctions will all be orthogonal with each other, with the only exception is if the two eigenfunctions are identical. So this brings us to one of the more wonderful features of quantum mechanics, and this is called orthonormality, and it's one of my favorite parts of quantum mechanics because it's going to make a lot of our calculations really simple. So a set of wave functions are going to be both, if a set of wave functions is both orthogonal, so their integral with itself goes to 1, and normalized, or sorry, orthogonal, so an integral in between two different functions goes to 0, and normalized, so the integral with respect to itself goes to 1, they're going to be referred to as orthonormal. Now let's express this in kind of mathematical senses. So I have in both cases the integral of the wave function of I with respect to j over all space. So it's going to be, for an orthonormal set, if I is not equal to j, so if these are two different functions, it goes to 0. If I is equal to j, so they're identical wave functions, then it goes to 0. Orthogonal, normalized, together gives us orthonormal. Now we can express this whole relationship with a single variable. It is called the Kronecker delta. So this is essentially delta ij. And if you ever see a delta ij present in an equation, this is another way of saying that the system is orthonormal. These two values are, if I is equal to j, 1. I not equal to j equals 0. So look for a system with a Kronecker delta, because then you don't even have to do the integrals. This is one of the reasons why we love orthonormality, is it lets us skip the complex math. And this is really where Dirac notation truly starts to shine. So using Dirac notation, what we find is that, again, if I'm applying wave function I with respect to j, it's going to be equal to Kronecker delta. And this is just always going to be the case. And so this is one way to really help us rapidly evaluate the energy of a system. Because let's say I apply the Hamiltonian with respect to j. Well, since this wave function is going to be an eigenfunction of the Hamiltonian, I just pop out the energy. The energy is an eigenvalue, so it pops out front. So then what I'm left with is essentially the Hamiltonian of this complex is equal to the energy times the Kronecker delta. So since both of these functions are the same, that means my energy is j. And again, you can also express this in integral form, though you'll notice it's a little bit more cumbersome. So this is one of the places where we tend to see Dirac notation really start to shine, is when we're dealing with eigenfunctions and eigenvalues. Because if I have an orthonormal set of eigenfunctions, well, if these two values are equal, I get the energy. If they're not, I get something else. And then what we really start looking at is to identify the patterns of our eigenvalues. Once you have those, a lot of the rest of our math becomes a lot easier. So now we've armed you with a basic set of quantum mechanical principles. Next time, we're going to go out and solve a simple system. On to the free particle. Until then, take care.